Hello world, it's Siraj and dynamic programming. It's one of the most important concepts in computer science. It's used all over the place in artificial intelligence, it's used in security, it's used in distributed systems, it's used everywhere. And in this video, I'm going to teach you how it works by going through several examples. But before I go through those examples, before I go over the abstracts, before I go over the theory, let's look at this demo I've got here. And what this demo is it's a visual way for you to see dynamic programming in action. What it's doing is it's aligning DNA sequences into this matrix, and it's a table, right, with rows and with columns. And what we can do is we can type in a sequence like A, let's say sequence 1 is going to be A, C, G, and they're all some variant of A, C, G, G, C, A, right? Those are the three letters. And then we can say A, G, C, A, G, C. And then for sequence 2, we could say, G, A, C, G, A, A, C, AAC, and so on and so forth. So notice how as I'm constructing these sequences, the table and the values in that table are getting filled in. What it's using is what's called a top-down approach. There's two types of techniques we can use in dynamic programming. A top-down approach and a bottom-up approach. And I'm going to talk about each of these in detail. So what I wanted to do was just kind of show you this visual demo before we go into the code. You can find the GitHub link in the description of this video if you want to look at the code, but it's a good way to visually see what's happening here, and it's all written in JavaScript. Okay, so what is dynamic programming, right? What is this? Well, there's this really famous quote by, I don't know who, it's not by dynamic programming, the concept, because concepts can't speak yet. Those who cannot remember the past are condemned to repeat it. That's some sage advice for you and for me as well. Jeez, oh my God. Anyway, so Bellman was the dude. Bellman made the Bellman equation, which is used all over the place in reinforcement learning. It's used for the Markov decision processes, responsible for some of the famous wins, AlphaGo, for example, in AI last year. But he had this very famous quote in the 50s when he created the concept of dynamic programming. And I'll quote him. He said, "Dynamic programming amounts to breaking down an optimization problem, ding, 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 AI, into simpler subproblems and storing the solution to each subproblem so that each subproblem is only solved once," right? So it's taking a big optimization problem. What is an optimization problem? It's a problem that looks to minimize or maximize some value iteratively, right? All of machine learning is an optimization problem, right? All of machine learning is trying to optimize to fit a curve. It's glorified curve fitting to some data. And dynamic programming is taking that optimization problem and breaking it down into simpler subproblems, okay? So that each subproblem is only solved once. Once we solve all of those subproblems, we can concatenate them or put them together to find the optimal solution for the larger initial problem. So what I've got here is this funny little it's like an XKCD, but it's not. It's just a clip. But what I'm going to do is I'm going to just animate the dialogue here just to give you some, a little bit of fun before we get into the harder stuff. So there's a woman and a man. Okay, so here's how it goes. "Oh, what to wear? What to wear? Such a vast wardrobe. How will I ever find the right combination? Perhaps I can help. Who are you? I'm here to tell you about Dynamix, the new selection optimization software from Algorithmic Anomaly. How does it work? Well, we use dynamic programming to recursively create an outfit that you'll look just stunning in. Now, if we want to do this in n squared time, we'll have to hurry. Let's begin. That shirt and those pants that you're holding, how good they look together. How would you rate them on a scale of 1 to 10? And so she says 7. He says, excellent, I'll enter that into our array. And then he keeps asking her these questions. How about those shoes with that necklace? She says 3. How about those other shoes with that shirt? She says 6. He keeps asking her these questions. This necklace with those pants, that shirt with those pants, 2, 6, right? 3 hours later, there, I've told you everything, and now in a few seconds, the paradigm will have worked its magic. Voila, all done. So what you want to wear are these exact pants, this shirt, those shoes, and that necklace. Later that night, darling, you look absolutely dynamic. Somehow I knew he was going to say that, right? So what's happening here is we took this larger problem, which is what is the optimal outfit to wear that's going to impress this dude at the end, right? And what this programmer did was he broke it down into subproblems. What's the optimal shoe and necklace to wear together? What's the optimal pants and shirt to wear together? And then he combined all those solutions to form the perfect larger problem, which is that larger outfit, right? So dynamic programming can be used to solve problems that would take exponential time, and it can solve them in n squared time or n cubed time. So it's very similar to the divide and conquer approach. Recall that in divide and conquer, we're taking a problem, we're subdividing it into smaller problems, right? We're dividing it and conquering each of them. But the difference between divide and conquer and dynamic programming is that in dynamic programming, some of these subproblems can overlap. And what I mean is, let's say this shirt, necklace, dressing example, we can have one of the subproblems be, what is the optimal combination of a necklace and a shirt? And another one could be, what is the optimal combination of a necklace, shirt, and shoes? Notice how the necklace, shirt, and shoes is kind of a subproblem of this other, not a subproblem, but a supersect problem of this subproblem. But they're both subproblems in the larger scale of things, right? But they overlap, is what I'm saying. So the basic idea is that in dynamic programming, we're breaking a problem up into subproblems, and we use the optimal solutions to those subproblems to give us the optimal solution to the larger ones. It's okay if they overlap, that's okay. And it's basically recursion plus using some common sense. So recursion allows you to express the value of a function in terms of other values of that function, where common sense tells you that if you implement your function in a way that the recursive calls are done and stored for easy access, it will make your program faster. So what we're doing with dynamic programming is we're essentially trading space for time, right? So instead of calculating all the states taking a lot of time but no space, we do take up space to store the results of all those subproblems to save time later. Right, so it's a trade-off. We're storing some values so we don't have to recompute everything all over again. So it's faster, but the trade-off is we're saving more data, so we're taking up more space complexity. A good time to use this is, check out this, here's an example, by the way. So the algorithm here is repeat the other's word, add your word, and pass it on to the next one. And if you're wrong, then you have to drink one beer and we start over again. So this is called dynamic drinking. It's just a joke, but it's like another way of understanding this. The first guy says while drinks, or the first guy says while, the next guy says while Bob, the next guy says while Bob ate. So at every iteration, we've saved the previous state, right? While Bob, think of it as an array, right? So we're storing all of these previous states rather than having to recompute everything all over again. And eventually this guy at the end, he's so drunk he forgets what the other said, and so we start over again. So all of these dynamic programming problems have 4 steps. First, we show that the problem can be broken down into optimal subproblems, right? So you have to think about it, like, right, in the case of dressing someone up, or in the case of some larger problem that we can subdivide into subproblems, like designing the optimal layout of a room, right? We could split the room up into subsections, right? And they all have their, individual and unique features, right? The wall is kind of curved at this end, but it's like this, and oh hey, this sofa would fit perfectly into this subsection of the room, right? So we divide it into subproblems. Then we recursively define the value of the solution by expressing it in terms of optimal solutions of the smaller subproblems. So the optimal solution to this room design problem would be such that each of these spaces, in terms of square meters or square feet, are filled at their maximum value, because the optimal solution for the larger problem is to fill as many square meters or feet as we can, such that the room is completely full, right? We compute the value of the optimal solution in a bottom-up fashion. I'll talk about that in a second. And then lastly, we construct an optimal solution from the computed information. Right, so here we go with this. There are 2 key attributes that we must have for any problem in order to apply dynamic programming to it. The first is it has to have an optimal substructure. What that means is an optimal solution to a problem, an instance, contains optimal solutions to subproblems. And then we have to have overlapping subproblems, meaning a recursive solution contains a small number of distinct subproblems repeated many times. So let's talk about this, right? So every problem has to have 2 of these features. It's got to have an optimal substructure such that for each of these subproblems, if we find the optimal solutions to them, we can combine them and then find the optimal solution to the larger problem. That's the first. The second is it's got to have overlapping subproblems, right? Like shirt, shoe, tie, and then shirt, tie, for example. Those are overlapping. So how do we solve this problem? Once we've identified a problem that has those two key features, how do we solve it? Well, we have two approaches. The first, and these are fancy words, is the tabulation approach. The second is the memoization approach. And what these really means are a bottom-up approach and a top-down approach. So here's the bottom-up approach. Let's say I want to become an amazing coder, right? That's the goal. So the bottom-up approach would be step 1, I'm going to learn programming. Step 2, then I'll start practicing. Step 3, I'll take part in contests. Step 4, I'll practice even more and try to improve. Step 5, after working hard like crazy. Step 6, I'll be an amazing coder. That's bottom up, right? We're starting at the very bottom. Started from the bottom, now we're here, right? We're starting from the very bottom like Drake, and we're going to the top. Now, top down is the opposite. We start with that final solution. I will be an amazing coder. How? I'll work hard like crazy. How? I'll practice more and more and more. How? I'll take part in contests. All the way down to the bottom, I'm gonna learn how to program, okay? Now I've got this table that shows some of the key differences and similarities between these two, which I'm not going to go into right now because there's a lot. Let's just get into an example, shall we? Okay, so for overlapping subproblems, let's take the Fibonacci sequence as an example. You've heard of the Fibonacci sequence, right? It's a sequence of numbers where every number in the sequence is the sum of the previous two numbers, right? So the first one will be 1, there's nothing before it, so it's 0. The next one is 1, so 1 plus 1, or 1 plus 0 is 1. The third one is 2 because 1 plus 1 is 2. The fourth one is 3 because 1 plus 2 is 3, right? It's just that chain, right? It's a recursive chain. We can solve it recursively. So that's the Fibonacci sequence. So how do we solve this? How do we write a programmatic algorithm for this? Well, one solution is to do it recursively, right? So doing it recursively does not mean doing it the dynamic programming way. There's a distinction here. So let's look at the recursive solution. The recursive solution looks like this in Python. Now let's go over this function here. The function is int fib with the parameter int n, right? So we input the amount of numbers in the sequence we wanted to compute. And then we have a base case. The base case is if n is less than or equal to 1, return what n is. And then return fib n minus 1 plus fib n minus 2, which are both the sum of the previous two numbers. So what this looks like is if f is 1, then we're just going to return 1. So then it would construct 1. If f is 0, then we're going to return 0, right? But then if f is 2, it's going to be this. It's going to be look at this recursive tree that's going to be computed. It's going to be f of 1 plus f of 0, which is 2. If it's f of 3, it's going to be f of 3 is going to be f of 2 plus f of 1, and then for f of 2, we have to then compute recursively the solution for f of 1 and f of 0. Now, if we do it like this, we'll totally solve Fibonacci. However, we're going to have to call f of 3 2 times if we do f of 3. We could have stored the value of f of 3 instead of computing it again, and we could have reused that old stored value. We're not storing anything in memory here. We're recomputing this entire tree. So notice if it was f, when I say f, I'm talking about fib. If f was like, say, 200, we would have to continually recompute all the branches of this tree of execution. Whereas if we saved some of these values iteratively, then we wouldn't have to do that. So right, it's a trade-off between time complexity and space complexity. So how can we do this in a dynamic programming way? Well, the dynamic programming way looks very similar to the recursive version with a small modification in that it uses what's called a lookup table before computing solutions. How do we do this? First, we initialize that lookup table as nil. There's no values in here. Whenever we need a solution to a subproblem, we first look into this lookup table. If the pre-computed value is there, then we return that value. Otherwise, we calculate the value and put the result in the lookup table so that it can be reused later. This is the dynamic version of it, the memoized version. For this function, we have our base case, which is the lookup table, initialized as nil. If the value is not calculated previously, then calculate it. Notice that here is the recursive part. Fib n1 with the lookup as its parameter, and then fib n2 with the lookup as its parameter again. We only add those up if the value in the lookup table is empty. And then at the very end, we return the lookup table. So notice how it is recursive. However, we're adding in this extra lookup table, which acts as a store for the pre-computed values in that Fibonacci sequence. And it's still a top-down approach, right? Memoized approach, because we're starting at the top. The top is what is the last value in that Fibonacci sequence, and then let's go to the smaller sub-values, right? Now instead of doing top down, let's do bottom up. So the tabulated or bottom up approach is building a table in a bottom up fashion and returning the last entry from that table. So for the same Fibonacci number, we calculate first fib 0, then fib 1, then fib 2, then fib 3, and so on, instead of the opposite way, right? So like fib 3, fib 2, fib 1, fib 0. We're doing it bottom up. We are literally building the solutions of subproblems bottom up. So in this example, for the tabulated version, we are starting with f of 0, right? f 0 times n plus 1. And we are adding, not subtracting from n, because n starts at that minimum value. And then we have our base case assignment, and then, well, n is going to be how many numbers we want. The parameter is the same. However, the way we're computing it is different. We're starting at the smallest value, and we're adding them up iteratively, like in this for loop. We're calculating the Fibonacci and storing those values inside of this array that we declared earlier. So both of these solutions store the subproblems, right? In the memoized version, the top-down version, the table is filled on demand, while in the tabulated version, we start from the first entry and all entries are filled one by one. But unlike the tabulated version, all entries in the lookup table are not necessarily filled in the memoized version, right? So that is the overlapping subproblems feature that each of these dynamic programming problems can have. Now here's the other feature, the optimal substructure feature. Now this also applies to the Fibonacci problem we just looked at, but I'm going to look at a different problem now, which really exemplifies this feature of dynamic programs. So the problem here is the shortest path algorithm, right? We know about shortest path, Dijkstra's. There's a bunch of the traveling salesman problem. There's a bunch of shortest path algorithms out there. But we're going to talk about one in particular that's called the Bellman-Ford algorithm. So let's say we have a graph, right? We have a graph, right? A graph with nodes, with edges, and we want to find the shortest path between two nodes, right? So how do we do this? So this is an example of a problem that has an optimal substructure. Check this out. I'm going to read this out. All right, here we go. If a node X, right, we've got a node X, lies in the shortest path from a source node U, right? We have node X, source node U, and a destination node V. That's it. That's all you have to remember. 3 nodes. Node X, node U, and then node V. Then the shortest path from U to V is a combination of the shortest path from U to X and X to V. Makes sense, right? We have 3 nodes. X is in the middle. U, X, V. All it's saying is the shortest path from U to X and X to V is equal to the shortest path from U to V. So if we solve these two subproblems optimally, we will get the optimal solution to the larger problem. What's the shortest path from U to V? Right? So that's an example. And we can use the Bellman-Ford algorithm to find that shortest path. So here's how it works. So we're given a graph and a source vertex SRC in that graph. We want to find the shortest path. Here's how we do it. First, we calculate the shortest distances which have at most one edge in the path. Then we calculate the shortest path with at most 2 edges and so on. 3 edges, 4 edges, 5 edges, etc. After the ith iteration of the outer loop, the shortest paths with at most I edges are calculated. And there can be at maximum v minus 1, where v is that highest threshold, edges in any simple path, and that is why the outer loop runs v minus 1 times. Right, so here's an example. We're computing all of these paths, and then we're finding the optimal solutions to those. Then when we find them, we can just add them together, and that gives us the optimal path from A to B, which are going to be our parameters to this model. So here's the code version of this. These are our initialization steps. We don't have to look at these, but here's really the meat of the code where this is happening. The Bellman-Ford equation finds the shortest distances from source to the initial node we were at. So step 1 is to initialize the distances from the source to all of the other vertices. Then we relax all the edges v minus 1 times. A simplest shortest path from source to any other vertex can have at most that many edges. So we have this nested loop where we're updating the distance values and the parent index of the adjacent vertices of the picked vertex. So consider only those vertices which are still in the queue. And then we check for negative weight cycles and remove them, so then we are left with the optimal solutions to that larger subproblem. And then we have, us constructing the graph with all of its edges and vertices, and then we print the solution. But I mean, there's literally a ton of dynamic programming problems out there. There's like 40, 50, 60 on these sites out there, like dynamic programming problems. There's 1,000,001 of these. Which I was looking at, geeksforgeeks.com. Check out geeksforgeeks.com. We've got so many of these dynamic programming problems. But anyway, where were we? Okay, so what do we know about dynamic programming? Any problem that dynamic programming can be applied to has 2 key features. It's got an optimal substructure, meaning if we can find the optimal solutions to the subproblems, we can find the optimal solution to the larger problem. And it's got overlapping subproblems, meaning some of those problems will overlap. Shirt, shoes, tie, tie, shoes, right? They overlap. And now where do we apply this? Well, in deep learning, the workhorse of deep learning is the backpropagation algorithm. This is how supervised learning works. Okay, let's take a look at some code here for this. Right, so here is a code for a simple feed-forward neural network that's trying to predict the pattern match between these inputs and outputs, right? We have 001, 111, 101, 100, and then we have its associated labels, 01, 000. We want to find the pattern here such that we give this network some input like 101 arbitrarily, and it will know exactly, oh, the label is going to be 0 or 1 after training on this very small 4-point data set. So how do we do this? Well, in this training step, we say first we initialize our weights as a matrix, right? We only have 1 set of weights. This is a perceptron, a very simple neural network. We have our activation function, which allows us to learn nonlinearities. And then I'm not going to go into the total details of backpropagation now. I've done this many, many times. Look at my Intro to Deep Learning series. In fact, I could just, rap about it a little bit right now. My ones and nos map to O's and ones, inputs, add weights, update, get sums, pass that shit to my sigmoid function, get that error, what's real in prediction, and that's why I use gradient descent. It gives predictions and it doesn't pretend. Update weights and repeat 10,000 times. Outputs are lit, I'll be doing just fine. If you want to see that actual rap, check out my Intro to Deep Learning playlist, and I think it's number 2, How to Make a Neural Network, where I actually rap that. But anyway, what we're doing here is we are calculating a gradient value, right? We're calculating a gradient value, which is also called a partial derivative with respect to our weight values. It's one single value, and we are doing that recursively for every weight going backwards. So we feed forward, we calculate some input data, apply an operation, right? Input times weight, activate, we send it to the next layer. Input times weight, activate, send it to the next layer. We get an output. We calculate the difference between the expected output and the actual output, the label. That's our error. We use that error to then compute a gradient with respect to the weights going backward, right? Backward we compute a gradient, we get that gradient, we update the weights at the very end. Then we use that gradient to compute the gradient for the next layer, and recursively for the next layer. That is dynamic programming, because we are storing that gradient value to update our weights later on, okay? That is dynamic programming. In principle, we could calculate the partial derivative of the function with respect to any weight simply by tracing out the nodes downstream from it and calculating the longer derivative chains manually. But we're not doing that. We're using the chain rule and dynamic programming to do it in a much more efficient way, and that is backpropagation. It would be very tedious to do it the other way. The key idea is that we can reuse results for an efficiency increase, just as we do for dynamic programming in general. So it's used in deep learning. Where else is it used? It's also used in reinforcement learning. In reinforcement learning, I've got a whole playlist on reinforcement learning as well. Just search reinforcement learning playlist Suraj on YouTube. But dynamic programming solves for the optimal policy or value function by recursion. So if we look at the landscape of reinforcement learning algorithms, we've got policy optimization and we've got dynamic programming. And two of the most important techniques in Markov decision process optimization are policy iteration and value iteration. And from them spring Q-learning and actor-critic methods. So dynamic programming is used heavily to find the optimal Markov decision process. And this, if you don't, if you want to know what a Markov decision process is, it's a way of framing an environment where an agent can learn from, right? We have a set of states, we have a set of actions that the agent can take, we have some transition function, we have some starting state distribution, a discount factor if we want to get fancy, and then some reward for completing the correct action, whatever that objective is. Lastly, let's go over some runtime analysis. How do we analyze the runtime of a dynamic programming problem? Well, it always takes this kind of formula. The pre-processing runtime plus the loop times the recurrence plus the post-processing. So it's the runtime of all of these. Pre-processing or any of the initial steps you have to take, just find the time complexity of that. For the loop is how many times does a loop run? Is it a single loop? Is it a nested loop? Is it a nested loop? And then recurrence, how much time does it take the recurrence to run in one for loop iteration? We multiply those two together, add the post-processing, and that's going to be our overall runtime analysis for a dynamic programming problem. I hope that video helped you, and if you want to learn more, please subscribe for more programming videos. For now, I've got to find 99 sub-problems, so thanks for watching.